Okay, so now we have laid down the prescription for a function of arbitrary period, reasonably well behaved function, periodic in nature, which can be written as a Fourier series. And we have also looked at the Dirichlet conditions which guarantee convergence. So it turns out that if a function is either even or odd, some extra simplifications arise, right? So which is the topic for this lecture. Okay, so a function is even if f of minus x is equal to f of x. It is odd if f of minus x is equal to minus f of x, right? So it's a familiar concept. So let's just very quickly look at a few examples. If f of x is equal to x to the n, then it's an even function if n is an even integer, and it's an odd function if n is an odd integer, right? You can verify this by plugging in the condition. Now if f of x equal to e to the x, then it's not even, it's not odd, it's not periodic, right? It's a strictly increasing function, right? E to the x. And on the other hand, if f of x is sine x, then it is odd, and not only odd, but it's also periodic, right? So this is the type of function which we are particularly interested in this discussion, right? So or f of x is equal to cos x is even, and it's also periodic, right? Hyperbolic cosine function is even, hyperbolic sine function is odd, right? Neither of these will be periodic, but they have oddness or evenness. Now any function can be written as a sum of an even function and an odd function, right? You may want to pause the video and very quickly provide a construction for how this is true, right, on your own, right? Or look at the argument that I'm going to give you. This is true because evidently you can just give a construction for it, right? So consider a function f of x and then build these two functions. One of them is, I'm going to call it f odd of x, half of f of x minus f of minus x, and f even of x, which is half of f of x plus f of minus x, right? Of course, not every function is either even or odd, right? This we have already seen examples of functions which are neither even nor odd. There are a lot of examples. You can construct your own, but you can always, given any function f of x, you can consider these combinations. You can evidently see that the first of these functions is odd and the second of these is even, right? You simply put minus x in place of x, then you will see that the first function there's going to be an extra overall minus sign which will come out in relation to the original function, whereas the second function, nothing changes if you change x to minus x. So clearly the original function itself is the sum of these two, right? You can immediately see this. So indeed any function f of x can be written as the sum of an odd function and an even function, right? So if you are able to, if you have some periodic function f of x, right? So working out the Fourier series of it, is a linear operation, right? So in fact you can work out the Fourier series separately for the odd part and for the even part. Oftentimes, this act of separating out the odd part and the even part is not going to give you any reduction in labor, but sometimes it gives you some extra insight, right? Because you see that cosines and sines have their oddness, evenness and oddness respectively, right? So in fact we will see that if a function is given to you that is odd and periodic, then it has properties, right? Let's look at periodic functions that are odd or even. If they are, then you have some simplifications. So if a function is odd or even, then we have this following integral, right? It doesn't matter in which interval you go from minus L to plus L. If your function is odd, then this integral is going to vanish, right? Evidently, because you just use the relation that f of plus x is equal to minus f of minus x, and then you break this interval from minus L to 0 and another interval from 0 to L, sum these two, and then you can quickly convince yourself that these two parts will vanish. And an even better way to do this is to actually do it graphically. Just plot a function which is sort of a mirror image of itself, to the left of the origin, but with a negative sign, and then you will see that the area that comes in on the right from positive x will cancel with the area that comes in from negative x. But on the other hand, if f of x is even, you don't have to do the full integral from minus L to L. You do, one of these parts, which is, let's say, from 0 to L, and then you just take twice of this, right? So that's a consequence of the evenness, right? So this result would be true no matter which interval that you consider. But if you are looking at a periodic function with period 2L, right, so it's natural to look at this entire interval for, which considers one full period of this function. Then the Fourier series we have seen, it has integrals of this kind. So it will lead to the following simplification. If f of x is odd, then all the ans will vanish, right? So indeed, so you cannot have any representation from cosines. If your function is odd, you cannot have any cosine part to it. It's going to have only it's going to be made up of a bunch of sines. And likewise, if your function of f of x is even, then it's all the bn are going to vanish, and the an are going to be given by this integral, right? 2 by L. Now the interval you need to consider is just 0 to L, right? So this is actually a direct consequence of this result, which I urge you to, use this result and in the prescription given for computing these coefficients for functions with period 2L, and then show for yourself that indeed these two results hold when your function is not only periodic, but it also has oddness or evenness associated with it. Okay, so many a time, right, so we had this discussion about piecewise continuous functions and piecewise smooth functions and so on, right? There was, at that point, it was just we're looking at some function which is defined in some interval a to b, right? And it's not necessary that, so there is any periodicity about this, but we can always, given, information about a function in some interval, we can extend this function such that, the function is odd, or you may extend this function such that it's even, or sometimes it makes sense to just extend this function as is, given whatever information is given, take that itself as the period and repeat it, right? So, there are contexts where, each of these is an actual thing to do. So let's look at an example. So suppose you are just given this function f of x in this interval, right? F of x is 1 from 0 to half, and it is 0 from half to 1. Now, if you are asked to expand this or extend this function such that you should be able to give a Fourier sine series for this, then you would extend it in a certain way, right? Such that it's going to be an odd function, right? Whereas if you want a Fourier cosine series, to represent its extension, then you would extend it such that it's an even function. Or if you just want to construct a Fourier series and assuming that this is one full period of this function, then that's the third kind, right? So let's look at all these three and you see how the Fourier expansion would change. If we must represent this function as a Fourier sine series, that means we must take it to be odd, right? And the interval is the period is 2, right? So from -1 to +1, right? Whatever information is given from 0 to 1. You must impose oddness to this, and so you say that you also have information for the value of this function from -1 to 0. So imposing oddness immediately gives you information about the value of this function from -1 to 0, and then you take this as your unit which repeats. And so if you do this and then carefully work out these prescriptions which are given here, then you will find that the odd extension of this function is 2 by pi, this whole expansion. So you can make a plot of this function and concentrate on the interval 0 to 1. It's going to agree exactly with this. Outside of that, it's going to get represented in a different way depending upon whether you have extended this function to be into a Fourier sine series, or if you do it in a cosine series, then you must make it to be an odd function, right? So now you'll get a different series. But if you take a close look at only the interval of interest, then it doesn't matter which of these you're looking at, they'll all give you the correct answer, right? So you need some input which is independent of this information on whether you want to extend your function to be an odd function or an even function, or just take this itself as the period, which is the third kind, right? So if you take it directly as a period, then in fact it's it's convenient to just look at the exponential series, right? So then you have Cn is given by this expression, and then like I said, it's always good to take special care for C0. So C0 you have to compute separately, and then you get a half, and then Cn is just 1 over I n pi if n is odd, and it is 0 if n is even and non-zero. If it is 0, then it is a half, otherwise it's 0, right? So the Fourier series in this case is, so you notice all these 2's here, which comes from this n pi by L, right? In this case L is a half, right? Whereas in the first two cases L is actually 1. So meaning this entire information from 0 to 1, you have to take a copy of this and paste it on the to the left of the origin, right? So minus 1 to 1 will be your period, whereas here in the third case you just take 0 to 1 itself as your period, and so in fact L in this case is 1. So so it's in fact L is equal to half. So the period is 1. So 2L is 1. So L is equal to half, right? So here it's convenient to work out this exponential series, and then we have this expression involving minus I 2n pi x dx. You have to be careful, and then the final result, because of these I n pi x by L, in this case L is a half, so you get all these factors of 2, and you have only these odd n's are allowed. So you'll see that this exponential series is going to be something like 1 over 2 plus 1 over I pi e to the 2 I pi x minus e to the minus 2 I pi x plus 1 over 3 e to the I 6 pi x minus 1/3 e to the minus I 6 pi x, and so on, right? So it would be an instructive exercise for you to take truncated versions of each of these series and plot them, right, using some plotting software. It doesn't matter which one, right? Use whatever is convenient for you, and then check that indeed all of them basically agree in this interval 0 to 1, right? Because they're all valid extensions of the same function, but you have input some extra ingredient in working out these different representations for this function, right? There are different extensions of this function. Okay, that's all for this lecture. Thank you.